So today's lab is probably something you wouldn't normally see in a statics class, at least not at this level. This is about determining whether or not you can actually solve a problem with the tools you've been given in this class. Almost universally, every problem that we've handed out to you guys in the course of this class has been solvable. What will happen when you leave here and you go to work, people are going to hand you unsolvable problems all the time. They just want the answer. And there's nothing wrong with that. There are other methods to solve these unsolvable problems, but they require much more advanced techniques. If you're a structural engineer or mechanical engineer, good chance you're going to end up using these tools in the future, those advanced tools. But you will definitely be taught this tool. And I'm going to, if you will, dumb it down for this lecture, just to make things a little easier. I'm going to start sharing my screen. And so we're talking about determinancy, and that's the ability to determine whether a problem is determinate or indeterminate and stable and unstable. Whenever a problem is either indeterminate or unstable, it will be unsolvable by the method you've learned in this class. So what I want you to be able to do at the end of this lab, hopefully, is to be able to recognize basic beam. We're not going to do about frames or trusses. That would be another level of things to learn here. But just a basic beam problem, whether it's determinate or indeterminate, when stable or unstable, so you know whether or not you can solve it. So, and when I talk about frames and trusses, those might be considered looking at determinancy as an internal problem, looking at the individual members of those frames or trusses. We're going to be looking at just external determinancy. So pretty straightforward, I hope. To determine whether it's determined or indeterminate, you guys already have the tools, really. And you probably have heard me harp a little bit about this, maybe not. But that in a 2D problem, you have 3 equations of equilibrium, and in a 3D problem, you have 6 equations of equilibrium. And anytime that you have more reactions than you have equations of equilibrium, it's going to be a indeterminate problem, i.e. unsolvable. And I've given a couple examples of that from the past, whether you remember or not, I don't know, but definitely have done that. So in this class, that's what we're doing, or this lab, I should say, is basically what it is. There's either determinate and indeterminate, and it's based on the number of reactions and the number of equilibrium equations you have. In this lab, we're only going to be looking at 2D problems. When we start looking at things like trusses and frames, just so you know, there would be something called equations of determinacy, and you would have to count the number of joints and the number of members, the number of reactions, and the number of loads, and then you would plug that into a calculation, and that would determine this for you. But anyways, here's a Class C example. This problem here, pretty straightforward looking, but as you know, we have 4 reactions and we only have 3 equations. So this problem is what would be termed indeterminate. You couldn't solve it because you would have 4 unknowns and only 3 equations. And so you wouldn't be able to do this without some more advanced techniques. If you want to know more about the determinacy equations, there's a lot of information out there to search, or you can send me an email and I'll send you some links on determinacy equations. But like I said, we're not going to cover that in this class because I think it's just going to would be too much. So just kind of give you a basic idea. So the next thing is whether it's stable or unstable, so the stability. And there are basically 4 ways that a problem can be unstable, even if it's determinate. So you might satisfy this determinant, i.e. the number of reactions is less than or equal to the number of equilibrium equations, but it might be unstable and therefore unsolvable as well. So some of this stuff, when you look at it, it'll be like, yeah, of course that's unstable. In other situations, it might not be so obvious. So of course, this very first one is there are not enough reactions. And here we would only have 2 reactions, and it would clearly not be a stable situation. And even though you have enough equations and you have enough reactions that it's determinate, it is an unstable problem, and you will not be able to solve this problem. Again, now this one in particular will not be solved because it's really not static.
I mean, why is it necessarily not static?
Well, if you look at this, try and take a moment at a couple places on this beam and tell me if you get the same answer, if it works out. Basically, there's no moment to restore anything here with a moment that's being created by the load. So it's going to move. There's nothing to counteract this force in terms of the moment.
Oh, I suppose if the bar has no mass.
Yes, we talked about that somewhere in the problem that the basic thing again is no mass. And to your point is that you would have to get pretty elaborate to figure out where that mass would have to be, and the mass would have to be perfectly there. So basically this is an unstable problem, not enough reactions. The next one is all reactions are parallel. And this, again, this is sort of the same problem, except for instead of in the moments, you now can't solve for any of the horizontal forces in the x direction. So again, this is pretty simple. You've got 3 rollers, 3 reactions. Again, qualifies as determinant, but clearly this is not going to stay put. It's going to shoot off to the left. So that's one of the ones is the reactions are parallel. All the reactions are parallel. So, and third, and this one is usually not quite so obvious, but you have to pay a little bit of attention to this one, is that all the reactions are concurrent. And you can see here, you've got these 3 balls. And again, we have 3 reactions, 3 rollers, excuse me. We have 3 reactions and 3 equilibriums. Again, it's determinate, but it's unstable. And while it might stay where it is, you could try all kinds of different loading configurations and it would not be solvable. As you can see with determinant, just so you remember what concurrent is, that means that the line of action of the reactions all intersect at a point. And it's important to say line of action because it's not necessarily that the forces are all pointing in the same direction. I could have put this middle roller on top and it would have had the same effect as having it on the bottom. Again, all the lines of actions would have intersected. So if this roller were placed off to the left or to the right, it would be solvable. But with that roller in the dead center, all of the reactions are then concurrent. And then lastly, and we won't be doing any of this in our lab, but I just wanted to show this to you because this is the 4th reason things would be unstable, is that there's some sort of internal collapse mechanism. And again, this one's fairly straightforward. If you look at this, it's a parallelogram. This is the same concept they use on bicycle derailleurs all the time, is a parallelogram to move the gears. And this thing, when pushed from this direction, is going to basically fall over. There's no restoring force, no restoring reaction. You could put another force over here and balance it. But again, we're talking about reactions and external, not internal. If we were looking at internal, what we would be doing is counting these number of joints, the number of beams, the number of reactions, and putting that into our determinacy equation and discovering whether or not it was stable, unstable, determinant, and indeterminate. So that's basically all the information you need to do this lab. There's not much to it, like I said, but I wanted students to see this. 1, because it's a nice, easy way to go out. 2, it's not something that you normally see in this class, but again, like I said, often in the future, you will be asked to do these kinds of problems that fall into these categories, and you're going to have to figure out what to do. what I often do in a lot of these cases is I either A, make assumptions, or B, I have to go on to the more elaborate methods to solve it, or C, just tell them it can't be done in a timely fashion. So, any questions at this point? All right, let's go on and look at the problem. So there are two parts to this lab. I can have, in the first part, there's 10 beams that you need to determine whether it's determinate or indeterminate, stable, unstable. And the second part is I want you to create some diagrams that meet those different criteria as stated, so that not only do you have that chance of looking at them, you know how to create stable and unstable and determinate and indeterminate problems. So you can download this file, which is everything that follows in this whole assignment if you like. You can have that as your own to work with or write on. Don't particularly care if you write right on the sheet that you print out. That's fine with me. The grading there's 14 problems, so we usually do this out of 10, so it's just going to be prorated to be out of 10, even though it's 14 problems. I'm not giving out any partial credit on these. These are either you got it or you don't get it. And each of the first 10 problems, I want you to draw a free body diagram separately and show the loads in reaction. I want you to state the number of unknown reactions in each problem. So again, you've been doing this all along. There's nothing new there. The only thing that's different now is that you're going to state whether it's determinate or indeterminate or stable or unstable. I misspelled that, so excuse me. Spelling has never been my forte. And the assumptions are is that the load is not orthogonal to the problem. That means it's somewhere between 1 and 89 degrees. It's not 0 or 90. The last one is that we know the geometry of the problem, angles and lengths, whatever. All that stuff is there, and that the beam is weightless, to Jason's point earlier. These are the diagrams of the types of connections that you're going to see in the next 10 problems. Just in case you've forgotten, the cable might be the only thing that is might throw you off. But here's an example. Here's the force. And it doesn't matter what the angle is, so long as it's not perpendicular or, really, so long as it's not perpendicular, not orthogonal to the problem. It's not 0 or 90 degrees. And then here are the connections. So that's it, pretty straightforward on those 10. So just go through and do those 4 pieces there, the free body diagram, the number of reactions, determinate, indeterminate, or stable and unstable. Now, do that. If we get down to the last bit, there are 4 different scenarios that I want you to create a drawing for. Please try not to just copy what's already been done. I know that there's a real temptation, but see if you can get a little creative and do it a little differently. This isn't a particularly lengthy lab, so I was hoping that you could try and get a little creative on this last part and come up with some ideas. All right. So that is pretty much it. It's pretty straightforward. Some of you should be able to finish this, I'm guessing, in half an hour. That's about how long it took me. I know that some of you are quite sharp. There's no doubt about that. So some of you might take a longer. I hope you'll get done. The lab is due at noon for the majority of the class. Those with, I can't remember the word, accommodations, have a little bit longer. But again, I can't imagine that you won't finish this task by the end of today's lecture. All right, I'm going to put you in breakout rooms, unless there's questions.